Thank you. Okay, hello everyone. It's great to be back in a presential event after all of this struggle, all of this time. So I'm very grateful to be here with you today. The introduction was already pretty good. So I want to still give you a bit of context on myself. My name is Javi, and that is my Twitter handle, and my dog as usual. And a few years ago, like 90% of my work was basically front-end stuff, right? Which is surprising if you consider the talk that I'm about to do. I wrote this material UI kit called React Toolbox, and I'm sorry if you ever used it because I abandoned the project. and I joined Vercel quite a few years ago when it was still called Zide. And since then I spent a lot of time working on APIs and tooling in general or internal developer experience. So in case you're not familiar with what Vercel is, it is the fastest way to deploy front-end applications. So we enable collaboration by giving front-end developers comprehensive tools to build high-performance websites. Our mission is to build a better web faster. With Vercel, you can connect a repository from any Git provider, and you would instantly generate multi-cloud deployments that are globally available through our edge network with every Git push. But if you're done, it doesn't ring a bell for you. You might know Vercel for being the company behind the super popular framework Next.js. All right, that's with introductions. So what is this talk about? From the title, it's going to sound like it's a very, very, very technical talk. It is not that technical. It's more about sharing a story, like sharing the story of our API. It all starts a few years back when we had a lot of microservices in a crazy distributed system that was very difficult to deal with. And building new stuff for that system was really painful. You're going to see why. So we ended up building a framework and then adding some extra tooling on that framework. And then the ultimate goal was to generate an OpenAPI spec for our API, which is why the talk is called like that. So what is the OpenAPI specification? Is anybody familiar with it already? I'm not sure about the background of you guys. OK, yeah, kind of, right. So the OpenAPI specification is an industry standard for describing modern APIs, right? And it's the most broadly adopted industry standard to describe APIs in a machine-readable format language. So it basically allows you to describe your API, available endpoints and operations, parameters for each operation, authentication methods, and metadata, like contact data, authors, and license, and so on. So why should we use that? And especially, why should we use it at Vercel? The most important reason to use this is that it enables static analysis. So you have a formal representation of our API, right? And you can pretty much build tools on top of it in order to do interesting stuff, like, for example, comparing a previous version of your API with a new version. And there's tooling already that would tell you if you are rolling a breaking change or if there is an unintentional change, and so on. So in our case, this is something really, really interesting because our API is open and it is documented. And we always want to have something that is really representing the real world, right? Without having to manually maintain it. So that's kind of the other reason. You can generate your docs, but not only generate documentation from the spec, but also you can generate a super nice documentation with embedded clients so that you can try out everything and you can try out requests and see, play around with your tokens and see what the response is going to be like. That's very interesting for a use case as well. And one that is like the most important for me too is code generation. So we have a dashboard that is consuming our API, and we have a CLI that is consuming the API. In both cases, we have developed client to talk to our API. If we get to have this this OpenAPI Spec representation for our system, we can get rid of thousands of lines of code just by generating a client, and not only that, but it can be generated in any language. That is really, really, really interesting. So where are we starting? Microservices, microservices, microservices. Probably all of you already heard of microservices and all of the pain that they brought into our developer world. In our case, we had a GitHub repository per microservice, an accountable developer per microservice, dependencies with NPM packages per microservice. And it was a code base written in pure JavaScript, so no types at all, no integration tests between services, because it wasn't that easy to make them talk to each other in a closed, containerized environment. So, I mean, just think about it. We were 6, 7 developers at the beginning working in the API, and you have like, I don't know, 40 repositories. So you have this bright idea, okay, this is actually not fine. We had, for example, database client that is shared between all of these microservices, and it's an external dependency. So you have this bright idea, okay, let's bump the version to a major one. You have to manually go to each of your 40 repositories or 30 whatever repositories and then change the package.json, yarn install, then I publish a new version, then I build it, then I roll it, repeat 40 times. That is incredibly painful, right? Sharing domain logic, this is something that probably nobody's going to tell you about microservices until you actually have to deal with it. But microservices are supposed to be about separation of concerns as well. But the reality is that you can end up very easily having some domain logic that you need to run in more than one service. And when that happens and you have separate repositories, and not necessarily even separate repositories, like separate systems, separate services, and you want to reuse that logic, it becomes a nightmare. Because if you're working with JavaScript, what do? In our case, we published private packages for our use case, right? And we had to inject dependencies into those packages. And those have peer dependencies to maintain and to bump as well. And they have to play together with a lot of microservices that have their own dependencies and their own package. So it's a terrible mess. So that you end up with code duplication. Because in the end, you have a piece of code and you're like, okay, I'm going to extract a package for this and publish a private package. Not really. I have to use this only in one place, so I'm going to just copy-paste this thing. And there's no homogeneity in the code base because different developers are working, although it's JavaScript, but maybe they are working in different repositories, different services, and you have freedom to choose whatever tool you want to use. So the code base is super diverse. And you work on some services, and then you jump into another one, and it's like a whole new world when it should be exactly the same. And there's no team visibility because separate repositories, easy to solve, but it was literally impossible to generate an OpenAPI spec. That was literally impossible. So we made a wish list. What do we want to have for a system? What would be like the ideal DX? We wanted to have a TypeScript monorepo. That's kind of okay, right? Reasonable. We wanted to be able to share code between each of our services. We wanted to make everything homogeneous. We wanted to have minimal roles, meaning that if I have a huge repository with tons of services and I want to make a change in a single file, I don't want to deploy the whole thing. I want to deploy only what changes, right? We wanted to have a single command to run the whole system. So you can containerize the thing and just do yarn deb, yarn start, or whatever, and then all of the microservices are going to be running in the same port. So orchestration would be very simple. And finally, culmination was we wanted to have generated documentation. But there was a very, 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 very important requirement for all of this. It has to be incremental. We need to be slowly bringing in changes over time and never stop working in the actual features that we are building for our customers. And this is really transversal. Everybody is suffering from this. Everybody knows that rewriting a system is a recipe for failure. There are a shitload of stories about it. So going back to our wish list, how do we make the whole thing incremental? First one, getting a TypeScript monorepo. Yeah, that is actually pretty simple. Because worst case scenario is a matter of getting a bunch of services and moving them all together, preserving the Git history into the same repository. And then you keep working and deploying in the same way. And you can adopt that incrementally, and you can adopt TypeScript incrementally. So you end up with a folder for each service, like deployments and domains and users, right? But code sharing is not that simple, right? First, you say, OK, we can have a global package JSON using Yarn workspaces or something like that, or Lerna. There are other tools for that too. But you can have like a global shared package for all of your services. So every dependency that is common to all of your services, you just keep it there. And that's pretty straightforward. Now, when it comes to sharing domain logic, you can extract a top-level folder or something. Just call it utils, pretty generic, right? And you can start adding stuff in there. And your services are going to be consuming it. But this is bringing a new problem, which is you actually have to embrace TypeScript, static typing, and have good tests, because the chances that you change the contract of line of code, the contract of a function, and it's affecting many places, and you break it and don't even notice, are quite high. But it's kind of OK. Like, you can go incrementally sharing code. So yeah, piece of cake, actually. Now, homogeneity is something that you also want to embrace in your new ideal system. And that is also quite easy. You can just share configuration for prettier ESLint or whatever, and then everything is going to be in the same style. At the same time, you can agree on certain utils. You're going to see in your package JSON dependencies that are doing the same thing, like different packages doing the same thing, just because there was more than one service using those dependencies. So you can identify that easily, and yeah, you can go there step by step. Now, minimal roles is something else, because how do you know what changed, especially in this scenario? So say that you have a file in utils that is being used in 3 different services, and then you change it, and then you push. How do you diff that code in a way that you know what exactly is what you need to deploy? It is outside of each service folder. So it's not really straightforward. Having a single command in this case, I mean, now it's doable because all of the code is there. But how do you approach that? Because you have a separate server for each microservice. And generated documentation is near to impossible to get it done, right? We didn't even think about it at this stage. So let's talk about how we get to minimal role single command. In our case, we were using a library, super minimalistic library called Micro. Micro is a layer that allows you to turn an async function into a HTTP server handler. The code would look like this. I said it wasn't going to be very technical. It's not super technical, but there are a few snippets. Not a lot of snippets, though. But if you look at that, it's quite straightforward. You can see that we are checking for the method, right? It's a get, right? If it's a get, I'm going to check the path name. Is the path name /user? Yeah, then I'm going to get user by name, and this is going to be my response. It is not. I'm going to check /user. That is routing. It's just routing, right? But because it is a microservice and it's so small, why are you going to bring in a library to do routing when you just need to check a couple of things, right? And if you think about it, HTTP, where you're going to have a request and a response, and you can reason about it like a function. It's simply a function. So the function parameters of that request are going to be the method, path name, the query string, some headers, and a body. And then the response is going to come with a status, and status text, headers, and a body. Those are like the parameters of your transaction, your function. So usually you can reason about it like method and path name, I'm going to use them for routing. I'm going to be using headers, query, and body as the parameters of my operation. And then I'm going to be responding with a code, body, and headers. OK. The path name, though, can include parameters as well. What do we do with those to decouple them from routing? When we parse it, we inject it into the query, and you're done. So reasoning about it and going back to our example, we can transform this. If we extract the routing logic, we can get to something like this. So what you have there is a couple of imports of handlers. Those handlers are going to have only the logic to handle our request without any routing logic at all. And we are decorating it with some functions that will act as filters. So I am composing a single handler out of two. And the first one is going to activate only when the HTTP method is get, and only when the path name is /users. From this, it is rather straightforward to get to something more static that is closer to configuration, right? So you can have a function from config that is going to receive that shape where you tell what is the method, path name, and handler, and it's going to be matching routes in a cascade. And the super cool thing about it is that it is completely static. It is serializable. You can run transformation on it. You can filter it. You can, analyze it. So the first iteration to start moving to an approach where we have a single server that can start all of our services would be something like this. We had a configuration file with all of the routes that looks like a manifest, basically. And then you can also tag it, adding tags to separate services. So you end up describing a single system where you have a bunch of path names, a bunch of routes, and handlers that are decoupled from the routing. And then you can group them in services. So with this, you can pretty much say, hey, I want to generate a server that works with only whatever is tagged as API user, and that is my user API. This way, you end up with a few interfaces that are quite interesting. First one there is you can run a server and build it in memory. So what we do is that we tell what is the route's path, we read it, we parse it, we remove everything that is not tagged as API user, and then we start a server in a random port or port of your choice, and we're going to get you the server running. That's it. This is super helpful for testing, for example, and to containerize your application and have a single container that runs the whole API, but also to build the microservice itself. Because in the same way that you have run, you can have build. And it's doing exactly the same thing. The only difference is that you're going to get that code, you're going to serialize it, and you're going to save it. And then you put it in a Docker container and deploy it, and that's it. That's your production service. And it's going to contain only what you need for that service. And not only that, but because you are dynamically building the entry point to your server, you can also have utilities to trace what is going on with that server and pretty much resolve the whole dependency tree. So you can tell it, hey, I want you to trace me the services that are built out of the API user tag for this configuration. And it's going to get you a bunch of, like an array of files telling you these are all of the files and modules that your service needs to build. And this is actually quite awesome. Because now, from this, it's more straightforward to build a GitHub action, GitHub workflow, where you diff with Git and get the file paths that change it. And then you can run for each of your services this command and then compare to see if anything that you're changing is affecting any of the services. And then you proceed and deploy only those, preview only those, and alert the developer, hey, you're changing this file in utils, and this is going to be triggering a deployment for 3 different services. And last one is that you can also build a CLI interface. So this beautiful world of doing in my local Journ dev, and I get 40 microservices running without dealing with Docker Compose and stuff like that, it is already there. Yeah, so we end up building this framework. And it's pretty minimalistic, very simple. Works from a command line and from Node.js. It can run your services, shut down your services on demand, trace the dependency tree of each service or a bunch of services together. They can still be contained and distributed independently. So you are preserving the goodies of microservices because you can scale them independently. And if one server goes down, your entire system is not going down, right? And you can statically analyze the whole system because everything is in a monorepo, and you are creating the entry points on demand with Typescript, which is statically analyzable. But there is still something missing here to make it everything like super standard. We already dealt with routing, and we know that the operation is going to be depending on our domain, right? Just in the handler, self-contained. And we are going to be sending out responses using send from micro, which is also traceable. But what about headers, query, and body? What about the parameters that are getting into the handler? And that is when you start thinking about validation. Each of our services had a different validation approach. That was pretty terrible. In some places, we were using a library. In other places, we were just doing a null check. Other places, we are checking directly the length of a string, for example. So what would be the perfect validator for us? Perfect validator would be one where you can describe rules in a serializable manner. So you can say, this is an object, has 2 properties. This one is required. You have the name has to have this length and whatever. That exists already. It's JSON schema. And there is a very popular validator called AGV that we can use for that. And it has pretty good default error messages, and it is also customizable. You can build better messages for errors, which is great. But there is a problem with that. AGV alone does not validate, does not output typed data. So if you're working with TypeScript and you are doing static types, after validating, you want to have the data already typed. So you know that if you're accessing a value that could be null, and it's not validated correctly, it would get you an error because you are accessing something that might be null. And fortunately, I stumbled up with this project, which is pretty awesome, from a guy called Thomas Aribart. This JSON schema to TS, pretty great project. And it basically round up the whole thing, right? Because now we can describe everything with a JSON schema, and we can get validated data that is typed. So everything comes together, and we can even customize error messages. So we end up with something like this for validation functions. You just have a validation like that. You pass the JSON schema, and if it fails, it's going to throw a known error. Otherwise, you get the data automatically typed. So you stop doing things differently in each service. And you can use this to validate body, to validate headers, the query string, to validate anything. So going back to our wish list again, we have a TypeScript monorepo. We have code that is shared between all of our services. Everything is homogeneous, so it's becoming homogeneous over time. We have minimal roles because all of our services are traceable. We have a single command to run the whole thing, but we don't have generated documentation just yet. So the time came here to think, okay, how do we deal with this? But everything was already TypeScript. And TypeScript is great because you can parse the AST and you can get types derived from your AST. It is statically analyzable, right? So you basically go through it with AST parsing utils, or maybe you don't even use utils at all. You just go with the TypeScript compiler. And you can trace the places where your function is being used. That means that if I am validating the query string, I can get at all of the places in a service where my validation function is being used and read the JSON schema. So there you go. That is the JSON schema for your query parameters in your system. So it's a matter of, tracing helpers usage. So we built some functions for validating the query, functions for validating the body, functions to validate the headers. And that way, we can pretty much analyze everything because we get the routing, we get the method, we get the path name, we get parameters, we can trace when we are sending a response with micro, what is the status code, what is the shape of the body, considering everything is typed. So in our use case, if we want to generate the OpenAPI specification from our framework, we already have endpoints and methods from the routes manifest. We already have path and query parameters from our validation wrappers. We already have header parameters from our validation wrapper as well. We can get responses from micro and resolve those types. And we can get metadata. How? Not sure how to get metadata. But it was already there too. JSDoc. So we can enrich our JSON schema with some custom properties and add some JSDocs to our functions. So an endpoint is going to end up looking like this. This would be a handler, detached from routing. So you can have a description. You tag a summary of what the handler is doing. You get the operation ID for later when you're generating code from it, so you can refer to it. You say what are the tags for it in order to generate more metadata for your spec later. And then you validate the query with a JSON schema, right? And then you send a response that is also tagged with the description of the response. And you can also add more descriptions, examples to the shapes that you are responding with. And out of this, we started getting handlers, putting these practices in place, running a command to generate the whole thing and analyze the AST, and we end up with a super nice new API documentation that is not yet released. It's going to be there very soon. But everything here is automatically generated. We even have an explorer so that you can paste your token and start playing around with our API. So, yeah, today we finish our wish list for API. And that helped a lot improving our DX, internal DX. Like we are able to ship much faster. It is very simple to write integration tests for a system. Everything became like super speedy. But there's even more to it. Because the goodies of having an output for the API that is statically analyzable is not ending with generating documentation and clients where you can remove thousands of lines of code in your code base. It's not only that. But also you can do stuff like this, which is pretty cool. You can build a workflow so that whenever somebody opens a PR in our API, we dynamically generate the OpenAPI spec only for the service that changed it, or maybe for every service. We compare them, and we can detect breaking changes. And if you are changing something at all in the API, we post a comment using GitHub Actions in our PR that is going to tell you, hey, watch out because you are maybe changing some deeply nested util that you don't even know that is somehow being used by these three services, and you're actually changing the response, adding a new property, or maybe something is becoming nullable. So, yeah, this is pretty good, pretty helpful. And if you get takeaway from this talk, you are always be hearing that people say, do not reinvent the wheel. Well, sometimes you're not reinventing the wheel. What you're doing is getting wheels together and building the vehicle you need. And that's all about it. Thank you very much.